Let's consider a coaxial cylindrical cable where there are just two shells. So here's the inner shell. Now this is very long, so I'm only drawing a small portion. And I have a current I flowing up that shell. And surrounding that is another shell. And that's, draw it like that. And on the outer shell, there's the same current coming down. Now, this is only a section of this cable, so we have a section here. And I'd like to calculate the self-inductance of this section. Now, again, there's two approaches, and I think you'll find when you calculate the energy approach, that's a little bit easier, because our magnetic field we can get from Ampere's law, and we pick an Amperian loop, and you can calculate the B field in here, B 2 pi R equals mu naught I. And so from Ampere's law, our B field calculation is not that difficult. And then we could, if we wanted to, and you will do this, is to calculate the stored energy, 1 over 2 mu naught B squared integrated over the volume. And when you think about a volume element, you could choose here a cylindrical volume element, which is 2 pi r prime dr prime h, if this section has length h. And then you could go and carry this calculation out. Now, what about the other definition of self-inductance, where we had L is the flux through the object divided by the current? Now, it's not so clear how to think about that. Here we have a B field directed like that. So what do we use? Now, this is a little bit tricky, but imagine that we considered a surface that looked like this. It was a rectangle that fit the size of this object. So that is our surface, this rectangle. Then we could calculate the flux through this rectangle where the element is just the B field times dr prime h over I. And we'll ask you to do that. But let's see what that means. Well, if we now said change the current and let I of t, say, increase, then we know if the current is increasing, this B field flux is increasing in the directions shown. So we would like a induced field, and I'll just write B induced, to oppose that direction. And so what we would get is, now imagine that our surface is actually a wire loop. And if this were a wire loop and there was changing magnetic flux, then we would get an induced current. So I induced would flow down the inner cable, opposing the increase of the current in the inner one, and up the outer cylindrical shell, opposing the direction of the current in the outer cylindrical shell. So we can use this area here to calculate our flux. Now, in a real coaxial cable where there's no loop, then all we're going to develop is an electromotive force between these two sides. Because the change in when the current increases, the change in magnetic flux creates an electromotive force, but it doesn't have a current path to establish itself. So this is a calculation that you'll do either way, with energy or with flux, and you can try this out yourself. This is a nice hint to get you started.